All set? Let's go. What I want to do now is I want to take what we looked at with the area underneath a curve, cutting it up into strips, and then using rectangles to approximate. I want to take all of that and I want to make it just a little bit more formal so that we can have a more formal definition of the area as a limit. So suppose we have a function y equals f of x, and we can see the graph of that function here. And we want to look at the region between that curve and the x-axis, specifically on the interval from a to b. So we're looking at the region underneath that curve, the area underneath that curve on a certain interval. Now, the way that we figured that out was we could approximate that by first cutting it into a certain number of strips. Some of the examples we did used 4 strips or 6 strips. And then we saw that the more strips we have, the better the approximation is. So we might use 10 or 100 or 1,000. And we would use rectangles to approximate those strips. And we can easily calculate the area of rectangles. So we could use that to get an approximate total area by adding up all of those approximating rectangles. And then that would give us a good approximation for the area under the curve. And if we take the limit as the number of rectangles goes to infinity, that will end up giving us the area if that limit exists. So I want to take that same idea, but I want to formalize it a little bit more with notation and different things like that. So what I want to do is I want to talk about the width of one of these rectangles or one of these strips. The whole width of the interval from a to b is going to be b minus a, right? We take the difference of those two x values to get the whole width. And what we're going to do is we're going to say that we have n strips or n rectangles. In this particular example I've drawn, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. But I'm trying to draw it so that it's a little bit more generic. We know the first 3 are going to be 1, 2, and 3. The last one's going to be n, no matter how many we've chosen, whether it's 9 or 15 or 1,000. And then we're going to say that a generic one in the middle we're going to call the ith strip or the ith rectangle. So we're generally going to use n for the last one and I for a generic one in the middle. Now, if we have n strips or n rectangles, then this whole width is b minus a. The whole interval length is b minus a. But if we're dividing that into n equal strips, then the width of each strip is going to be b minus a over n. And what we're going to do is we're going to call that delta x. Delta x kind of generically means a small value, kind of a small width of x or a small change in x. And so we're going to let that be the width of one of the strips. And we said that to calculate that width, we take the whole width of the interval, which is b minus a, and then divide by the number of strips, where there are n of them. And so this is the width of a strip. A strip or a rectangle. Remember, we cut it into n equally wide strips, and then we use rectangles to approximate. So that's where we're at. You can even, if you really wanted to, put in some rectangles. I'm going to do some left-handed rectangles, just because if I did a right-handed rectangle, I would kind of draw in the middle of this S sub n. So not a real important reason. But remember, we're not just cutting them into strips. We are eventually then going to use rectangles to approximate those areas. But anyways, we have the width of our strip in terms of the endpoints of the interval and the number of strips or rectangles that we're using. And what this does is it divides things into n strips. And if we look at those strips, they're all parts of the interval from a to b. And specifically, if we let a be x sub 0 and b be x sub n, then we're basically cutting this interval into n subintervals. We go from x sub 0 to x sub 1, and then the next one is from x sub 1 to x sub 2, etc. And then the last one is going to be from x sub n minus 1 to x sub n. Right, there are n strips, and the last one ends with x sub n, and then it starts with x sub n minus 1. So that's kind of how we're breaking down these intervals. And we can actually write out an expression for any of these points, x sub 1, x sub 2, x sub 3, x, etc. If you look at x sub 1 specifically, that is this one right here. Well, we start off with a, and then we've added the width of the strip. But remember, the width of the strip is delta x. So that's going to be a plus delta x. And then x sub 2 is going to be a plus 2 times delta x. Because x sub 2, we've started at a, and we move over 2 times the width of the strip. And we could also say x sub 3 is a plus 3 times delta x. And if we keep going, for any generic strip in the middle, x sub I, that's going to be a plus I times delta x. So we've got the width of a strip or a rectangle as delta x. And then this is a formula for the right endpoint of the ith strip. Strip or rectangle, same difference. And so if we want to write out what our approximation of the area was with right endpoints, we could write this as f of x sub 1 delta x plus f of x sub 2 delta x plus dot 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 all the way up to f of x sub n delta x. And this is called a Riemann sum. We haven't actually given a name for this yet, but I think now is a good time. A Riemann sum is basically a way of approximating the area under a curve by using rectangles. And so you're adding up the areas of the rectangles, and each one is the height of the rectangle, which is a function value, either on the right side or the left side or the midpoint, or it doesn't really matter, but the height comes from some function value, and then the width is going to be delta x. And we actually can say exactly what all of those x sub i's are in terms of a and I and delta x is in terms of b and a and the number of rectangles. So this is actually a formula in terms of the two endpoints, a and b, the number of rectangles n, and adding up all of those things together. Even though you don't see a, b, and n in here, all of this goes down to those things. So what we have here is a nice formula for an approximation of the area in terms of the endpoints and the number of rectangles and, of course, the function. And we've said that the area is defined as the limit as n approaches infinity of this sum. Because that's the number of rectangles increasing, getting more and more. It gets closer and closer, a better and better approximation, and the limit gives us the area. So this is the same as the limit as n approaches infinity of f of x sub 1 delta x plus f of x sub 2 delta x plus dot 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 all the way up to f of x sub n delta x. That is a lot to write out. We're going to, in the next video, look at a way to write this in a little bit more simple way, a different notation. But I want to say just a couple of things first. First, it can be proved that this limit exists so long as the function is continuous. So if we are ever looking at continuous functions and wondering if we can calculate an area, if this limit will actually exist, it will for continuous functions. There are other families of functions that it also exists for, but we're just going to focus on continuous ones here. Another thing that can be shown, right, here we picked right endpoints, but we also looked at examples with left endpoints, and it can be shown that if you replaced R sub n with L sub n, you would get the same answer, right? We get the same answer if we pick right endpoints or left endpoints. We get different approximations with each of those, but those approximations approach the same limit. And in fact, it can be shown that we get the same answer if we pick any point in each subinterval. We don't have to pick all of the left-hand endpoints. We don't have to pick all the rights. We don't even have to pick all the midpoints. You could choose randomly any value in each of those intervals, any sample points, and you could evaluate this limit. And so long as the limit exists, the limit is going to be the same no matter which. And because of that, it doesn't necessarily make sense to define this in terms of those right endpoints, because it's equally valid to use the left ones or the midpoints or kind of any. And so we're going to have one more definition here. And instead of picking left endpoints or right endpoints, etc., we're going to pick sample points in each interval. So if we use sample points, and we can call those x sub 1 star, that's a sample point in the first interval. X sub 2 star is a sample point in the second interval. X sub 3 star is a sample point in the third interval, all the way up to x sub n star. We can pick any sample points in each of those intervals and define the area to be the limit as n approaches infinity of that sum where we take the first sample point and we multiply it by the width delta x plus the function evaluated at the second sample point times delta x plus ... all the way up to the function evaluated at the nth sample point times delta x. This is a more generic version of the definition, a more general version, instead of just picking the right endpoints, because it might not be that those are the most convenient points to pick. There might be other points that are more convenient to pick. And so, kind of more generally, the area underneath a curve is defined as this limit where we can pick any sample point to evaluate the function to give us the height of the rectangle for each interval. All right. I know that seems very abstract. We've got all sorts of variables and we've got subscripts and we have asterisks and everything, but this is a math class. We do want to go through things very rigorously. We don't just want to look at some examples. We want to look at proper definitions. And so that's kind of the point of this, to really formalize all of the things that we've been looking at recently with these areas.